Okay, let's go for the next topic, magnetic forces and current carrying conductors. Imagine that we have this magnetic field, it's constant, and we have a conductor, a wire with a current I. The length of the wire is L. Okay, now let's try to find the force acting on this wire, right? Because the charges are moved or the current is present in the wire. Remember, we found that when we have a charged particle, by convention is a positive charge, moving inside of this constant magnetic field. We found before that there is a force acting on this charge, and the force is perpendicular to the velocity and also perpendicular to the magnetic field. To do that, we use the right-hand rule, right, to find the direction. In this case, it's going to be the magnetic field in this direction, the velocity in that direction. So the force is acting in this way, and the path is going to be a circular path. We found this before. Okay, this is the case when we have one charge, and charge Q, right? And the force acting for one charge is equals to the charge times V magnetic fields V sine theta. Okay, now in this case we have a bunch of charges, right? The current inside of the wire. Remember, we also found that if we have a conductor, we have charges moving, right, with this velocity, the drift velocity. What we found, if this is the area right here, well, it's gonna be the charge density, the current density, correct? Current density. Okay, that involves the current and involves the area. Okay, also we have the drift velocity. Okay, now in this case, when we're dealing with a conductor, this velocity is gonna be the drift velocity right here, right? And the charges, right, is gonna be the sum, or the charge is gonna be the sum of the charges in the conductor. Okay, now let's see what happens. In this case, this formula takes this form. It's gonna be the sum, right, of all the charges times the magnetic field times V. In this case, it's gonna be the drift velocity times sine theta. Correct? But how do we define this drift velocity? From the figure, we can see that the drift velocity is equals to L divided by the time. Correct? Perfect. So do we have, this is the sum, okay, of all the charges times V times L over time sine theta. Let's place this quantity right here, and what do we have? This is equals to sum of the charge divided by the time times V times L sine theta. Correct? And what is this? That's the charge. That's the total charge. So it's equals to, in this case, the current, right? The charge divided by is the total current, correct? The total current times B times L times sine theta. And this is again the force acting on this segment of the conductor is equals to current B times L times sine theta. Also, we can represent this in this way: current L now is a vector cross product with the magnetic field. Okay, perfect. Now, also right here, remember, in this case, the current is equals to N, the numbers of particles per unit volume, times the charge, times the drift velocity, correct, and times the area. Okay, great. So in this case, we have the current gonna be N, charge, drift velocity, right, times the area. Perfect. We know also, right, that if we have a wire, one more time, a wire right here, and we have this being the magnetic field. If there is the current, if the current is zero, well, nothing happens. But what happens if we apply a current in this direction? What happens in that case? Well, we use the right-hand rule, right, to find the direction of the force. In this case, we have this is the direction of the magnetic field. the direction of the current. So this the force acting on this wall is gonna be correct in this direction. Correct? We have a force in that direction. Correct? If the current goes opposite direction, well, it's gonna be in the opposite. The force acting right in the opposite direction. Correct? Perfect. Now let's see what happens if we want to create torques using the same analysis. Well, let's do it. Let's work with torque. Right, when we have a wire, a conductor, right, inside again of a constant magnetic field. And the topic is gonna be torque on a current loop. Okay, torque on a current loop. Okay, perfect. Imagine this is the loop right here. This is the loop. It's a rectangle. Imagine it's a rectangle like this. Imagine now that it's allowed to rotate through this axis right here in this way. Okay. Imagine that this length is L and this width is W. And now we have a magnetic field acting in this direction. Correct? This is the magnetic field and it's constant magnetic field. And also we had current in this direction. Imagine current in that direction. So now let's find the force by acting along this loop, applying right this equation. Okay, perfect. Let's go to this segment, right, the horizontal segment. Well, in this case, the current and the magnetic field are parallel. If they are parallel, right, the angle is 0, and sine 0 is gonna be 0. So there is no force acting on this segment. The same thing happens right here, right? On this horizontal segment, the force is 0. Now, what happens on this vertical segment? Okay, in this case, in the magnetic field, right, if the magnetic field goes in this direction and the current goes in this direction, so there's a force right in this way. So we have a force on this segment pulling right this segment or the loop in this direction. What about right here? Well, in this case, we have the current going up, correct? So the current is going up and we have the magnetic field in this direction, the current goes up, so the force goes right into the wall, right into the wall. So we have one force coming out from this wall, right? And right here is going into, so we have a torque, right? We have a torque. Okay, now let's find the magnitude of that torque that is acting on this loop. Let's do it. How do we define torque? Torque is defined as in this way. This is tau. That's the symbol for torque. Tau equals to R cross F, the cross product. So this equals to R, right, times force times sine theta. Okay, from this picture, well, from this picture, this is, remember, R is the distance. Remember the picture that we used before when we're dealing with torque. Imagine this is the case. This is a disc that is rotating through the axis or through the center, which is the axis of rotation. Imagine that we apply a force in this direction, and we apply a force in this direction. Imagine forces. If the forces are first 1, okay, net 2. If these forces have the same magnitude, look in the same direction in this picture, that produces not rotation, not torque. Correct? Because they're opposite. Well, they're the same, right? But they produce an opposite rotation. In this case, one produces clockwise rotation, the other one counterclockwise. But the magnitudes are the same, so they cancel each other. But what happens in this case? If this is in this direction and one in the other one is opposite direction, correct? What should be the net torque? Well, in this case, we have a clockwise rotation. We have a net torque. What should be the net torque? The net torque is gonna be R1 right cross F1, correct, plus plus R2 cross F2. And well, in this case, well, R is the same, the magnitudes are the same, and it looks like it's gonna be twice this product, correct? It's gonna be equals to, because these R are the same, R1 and R2 are the same, the forces for this particular example is the same, so then it's equals to what? Twice RF sine theta. The same thing happens right here. So we have one force acting in one direction, acting in opposite direction, right? The magnitudes are the same, so we create something like this right here. Okay, let's do it. So again, what should be the net torque? The net torque is equals to R. What is R? R is the distance from the axis of rotation, right, to the point where we apply the force. This is R, which is gonna be omega divided by 2. And what should be the force? The force is this force right here, correct? So the force is equals to current, right, B times L. Okay, let's do it. So do we have this equals to omega divided by 2 times current VL sine theta plus, this is the force, the torque produced by this force right here. Now what happens in the other side? Well, we have the same thing, correct? Divided by 2 current VL sine theta. Okay, and what it is, this is equals to, look, current, because it's not the same, these two are the same, right? This is just the current times V times omega times L times sine theta. But what is this quantity? This quantity is this product, right? Omega times L, that give us the area, right? Area is equals to L times omega. Okay, perfect. From here we can say that it's equals to current magnetic field area sine theta. And this is the torque acting right on any loop with a current. Okay, and what do we have? This is torque is equals to the current times the magnetic field, correct, times the area times sine theta. Also, if we have n loops, it's gonna be just n times the current times BA sine theta. Correct. Also, we can represent this because we have sine theta and vectors. We can represent this as equals to n current times area cross B. Correct? And these two are the same. Again, this is the formula that is found when we're dealing with torque on a current loop. In this case, N is the numbers of turns, right, for the loop. Correct? Okay, perfect. Now let's go to find the magnetic dipole moment in the way as we did for the electric dipole moment. All right, let's do it. They have the same form, right? These two dipoles. So let's go to the magnetic dipole moment. Magnetic dipole, right, moment. Correct. This is similar to the electric dipole moment. Remember when we have this dipole moment, where we found that this is P, correct? And we found that the moment P was equals to, we call this the distance times the charge. In this case, for the magnetic dipole moment, well, the same idea. We have a magnet, where this is north, this is south, and we place this inside of a magnetic field. So we know that it becomes aligned, right, because of the forces acting. So there's a torque that aligned the the magnet to the magnetic field. Perfect. And the same thing as for the electric moment, we define the magnetic dipole moment in this way. It's going to be mu as a vector equals to n numbers of the turns times the current times the area. Now the area is a vector, remember, it has a magnitude, right, and the direction. How we can find the direction, for example, of the area of the direction of the magnetic dipole moment in this way? Imagine that this is the current in this direction. So we use again the right hand rule, right? If this is the direction, the thumb, right, represent the direction of this magnetic dipole moment. Correct? Perfect. Now, that definition, when we apply that definition, right here, what do we have? Well, torque, now tau is a vector, right? It's a vector. Well, it's not a vector, right here is a vector, right? A vector. This equals to mu, right, cross the magnetic field, where mu again is the magnetic dipole moment equals to n current times the area. Correct. Also, it's found that using the electric dipole, from the electric dipole, right, the torque or tau is equals to P, right, which is the electric dipole moment, cross the electric field. Correct. And this is the electric dipole. Correct. We can do the same thing for what we did is actually, right, the same thing for the magnetic field in this way. Also, we have the energy of this electric dipole is defined as negative P dot, right, the electric field, correct? This is the potential energy of the electric dipole, right, potential energy. Because they have the same form, the same thing happens to the magnetic case, right? This is equals to negative, right, the product of these two vectors. And now this is gonna be the potential energy, correct, of a magnetic dipole, right, in a constant magnetic field, right, in a magnetic field, correct. And again, we create the same formulas as for the electric field. Now we have the magnetic field, right, what is similar to the electric field, using the torque and using the potential energy. Okay, and with this we finish chapter 27, right? And let's go for the next chapter. Okay, thank you and see you later. Bye.